Hi everybody, welcome back to a concept session. In this we will discuss magnetism and matter, electromagnetic induction. First, magnetism and matter. This includes bar magnet and its properties, magnetism related Gauss law, magnetization and magnetic intensity, magnetic properties of materials, and geomagnetism also we will discuss. Let's go. Magnetic length, the shortest distance between the two poles. Actually, for a bar magnet, it is 5/6 of a geometric length. For only bar magnet it is. For other magnets, this rule won't hold good. Magnetic length is always treated as 2L. From center to one end is L, from center to another end is L. So 2L. And pole strength of the magnetic pole is strength of the pole that getting attracted or to attract another pole. Magnetic moment M is pole strength into length of the magnet. Length of the magnet refers to 2L only always. So 2L into pole strength. 2L into pole strength gives rise to magnetic moment. Pole strength units ampere meter. Moment units pole strength unit ampere meter. I want to write with another color. Unit ampere meter. Its unit ampere meter square. Moment units ampere meter square. Oh, I typed. Magnetic moment is a vector quantity. Pole strength is a scalar quantity. Here I didn't write. This is a scalar quantity. Scalar, but it's a vector quantity. Vector quantity. Okay, and south to north and away is the direction. Here is combination of two magnets. When like poles are in contact, then formula is square root of m1 square plus m2 square plus 2m1 m2 cos theta. When unlike poles are in contact, square root of m1 square plus m2 square minus m1 m2 cos theta. If both m's are equal, then it will become 2m naught cos theta by 2. This is 2m naught sin theta by 2. Cutting a bar magnet. If you cut the bar magnet in equal parts parallel to the length, lengthwise if you cut, cross sectional area of the bar magnet will change the piece. That means I'll show you like this. If a bar magnet is cut like this, it is cut like this, then cross sectional area becomes, this is a by 2 and this is a by 2. Then obviously pole strength will be m by 2 and m by 2. If it is cut n parts, then obviously m by n, that is this. And length will be same only. Moment will be m by n. Moment will become by n and pole strength will become by n if you cut like this. If you cut perpendicular to the axis, that means if you cut like this, then pole strength remains the same. That's what. And this is 2L by 2 if it is into two parts. For n parts, 2L by n. And moment will be m only. M dash is equal to m by n. Bending a bar magnet. If you bend a bar magnet, then two poles will come closer. Automatically moment will change. So bending a magnet changes the moment. If you bend a magnet into a arc of radius r and angle theta, then its a new moment will be old moment m, then new moment will be 2m sin theta by 2 by theta. Theta must be in radians. Theta must be in radians. And if it is bent into semicircular arc, then this answer will come 2m by pi, semicircular arc. And if you bend a quadrant of a circle, then its value will become m sin theta by 2, theta 90 degrees if you put, then m sin theta by 2 by theta also should be 2m sin theta by 2 by theta. So 2m sin 90 by sin 45, 1 by root 2 by theta is pi by 2. So it will be 2 will come, this 2 will go. So 2 root 2m by pi is the final answer. This is an unsimplified answer it is. Okay, 2 root 2m by pi is the answer. Next. Magnetic induction. B. Force experienced by the unit north pole. Magnetic induction is defined as force experienced by a unit north pole. Yes, just like electric field intensity, force experienced by unit positive charge, here unit north pole. and B bar equal to F by M or F equal to MB. When a pole of M strength is placed in a magnetic field B, then force is equal to F equal to MB. SI unit of magnetic induction is Tesla. SI unit of induction is Tesla, Weber per meter square. 1 Tesla is equal to 10 power 4 Gauss, and magnetic induction at a point due to pole strength B is mu naught by 4 pi M by D square. M at a distance D, mu naught by 4 pi M by D square. So I can simply call like this. B has 3 formulae actually. One is F by M naught. This is test pole, or mu naught by 4 pi M by D cube. Whose pole? That's one. D square only, because B only, no. And the third one is flux density phi by A. That also will come. So 3 formulae are there. Magnetic flux phi BA cos theta. It's a scalar quantity. Flux density is known as magnetic field induction again. No two lines of forces intersect. That also we understood. Gauss law in magnetism. Gauss law in magnetism is total net flux coming out from a closed Gaussian surface. Closed surface only called Gaussian surface is in electricity 1 by epsilon naught times of charge enclosed in it. But here don't think that 1 by mu naught times of pole inside. Pole inside will be actually north pole present, south pole immediately will be there. So net outward flux, net inward flux for any Gaussian surface for magnetism will be 0. So obviously net flux is equal to 0. This is second law of Maxwell's equation. Maxwell's second equation. Inverse square law, F is equal to mu naught by 4 pi M1 M2 by D square when they are separated in a particle free space, where D is separation between poles. Mu naught is constant known as permeability of free space, and its value is mu naught equal to 4 pi into 10 power minus 7. Henry per meter is the unit for that. Relative permeability is mu by mu naught, and mu is absolute permeability of the medium. Mu naught is free space permeability. And relative permeability won't have any unit because it's a ratio of same kind. Magnetic induction at a point on axial line of a bar magnet is, if it is a short magnet, if it is a long magnet, 2 formulae will come. If it is a long magnet, 2md by d square minus l square whole square with mu naught by 4 pi quotient. This is long magnet. If it is short magnet, just 2m by d cube. Yes, 2m by d cube. What is this A? There is 2m by d cube. Yes, there is no A here. And what is this M? Let me correct it here only so that it will be good. Otherwise, very clumsy. For a short bar magnet, just it's a small correction. Let me make it here. Yeah. Yes, 2m by d cube. Correct. Magnetic field induction on an equatorial line, mu naught by 4 pi m by d square plus l square whole power 3 by 2 for long magnet. If it is a short magnet, just m by d cube. That is 2m by d cube. This is m by d cube. And direction of B is in opposite direction of magnetic moment M. And angle between M and B. M and B is 180 degrees. M and B is 180 degrees. Here it's missing. Next. Null points are neutral points. Actually, whenever combination of field exists, that means 2 or more magnets are present, then their combination field will exist at a place. So in that combination field, the combined field due to several magnets or magnetic materials, whatever producing magnetism, may become 0 or may not. If it is equal to 0, then such region is known as null region, and that is only null point actually. So it is a point at which resultant magnetic field is 0. If two like poles of strength M1 and M2 are separated by distance d, then the distance of null point from weak pole M1 is x is equal to d by square root of M2 by M1 plus 1. Null point lies between poles, not what you call. If two unlike poles of strength M1, M2, then null point is given by x is equal to d by square root of M2 by M1 minus 1. Root is up to only M2 by M1. Okay, plus or minus 1 will be outside story only. When north pole of a bar magnet faces geographic north, then null point comes on the equatorial line. This is important. When north pole of a bar magnet faces geographic north, null point comes on an equatorial line, mu naught by 4 pi m by d cube. And where BH is equal to horizontal component of Earth's magnetic field, m is magnetic moment of a bar magnet, separation between center of bar magnet and null point. When S pole of a bar magnet faces, south pole of a bar magnet faces geographic north, then null points come on axial line. So mu naught by 4 pi 2m by d cube will be equal to BH at the null point place. Torque acting on a magnetic dipole placed in a uniform magnetic field. When a magnet is placed in a uniform magnetic field, then it will experience torque. The torque tau is equal to mb sin theta or m bar cross b bar. M bar cross b bar. Couple or torque. mb sin theta is the magnitude, vector from m bar cross b bar. At equilibrium for the following arrangement. M1, M2. Angle will be theta. M1b sin theta 1 equal to M2b sin theta 2. Theta 1 is with one of the magnet, theta 2 is with the other magnet. Combined magnets suspended in a magnetic field B, then it will be in a resultant position that theta 1 will be with M1, theta 2 will be with the other one. Potential energy of a bar magnet is, the potential energy stored in it is U, that is equal to minus m bar dot b bar or mb cos theta. And theta is equal to 0 degrees, stable equilibrium. Theta will be 180 or other will be unstable equilibrium. Work done in rotating a magnet is W equal to mb of cos theta 1 minus cos theta 2. This is when a bar magnet in a magnetic field rotated from theta 1 to theta 2, then work done is equal to mb of cos theta 1 minus cos theta 2. And when theta 1 equal to 0, theta 2 is theta 2 is theta, theta 1 is 0. That means from equilibrium position to it is deflected through an angle theta, then mb of 1 minus cos theta, frequently used formula. Next, the time period of an oscillating magnet in an external magnetic field B is given by T equal to 2 pi root I by mb, where I is moment of inertia, m is its moment, and b is the external magnetic field. And moment of inertia is ml square by 12. L is geometric length of a magnetic needle. When magnet is cut into n parts perpendicular to its length, L dash equal to, this is I dash actually, I dash is equal to I by n cube, or T dash, time period is equal to original time period by n. And if the magnet is cut into n parts along the length, if it is cut along the length, then time period remains unchanged. I mean to say, suppose one bar magnet is there and is giving a time period t, the same bar magnet is cut into two pieces, suppose two pieces along the length, and this piece is used, then its time period is also t only. If this piece is used, that also t only. Whole magnet is used, then also t only. That's what the second statement's meaning. If magnet is cut along the length n pieces, then moment of inertia by n, and moment also becomes by n. So obviously time period remains unchanged. Numerator become by n, moment become by n, so remains same time period. Intensity of magnetization. Intensity of magnetization means how much magnetism attained by a material, that is pole moment developed per unit volume or pole strength per unit area. I is equal to m by v, r is equal to m by a. Intensity of magnetic field or magnetizing field intensity. This is applied field intensity, applied field. This can be given as H is equal to H, this is represented as H is equal to B by mu or B naught by mu naught. That means free space induction by that space constant, permeability, and any medium induction by that permeability. And for vacuum, I is equal to, this is something irrelevant mixed here. B is equal to mu naught H, correct only. Okay, these things only typed here. This I want to remove. B equal to mu naught H. Okay, fine. Magnetic susceptibility. It is the ratio of applied magnetic induction intensity to the, attained magnetic field intensity to the applied magnetic field intensity. Nothing but intensity of magnetization by intensity of magnetic field. So I by H is susceptibility chi. It has no units. Then diamagnetism, diamagnetic substances. Diamagnetic substances are those elements not having net magnetic moment. If net magnetic moment is zero, then such materials are diamagnetic. Bismuth, copper, lead, silicon, and there is a close relation between diamagnetic materials and a physics student. The thing is, copper get repelled to the strong magnetic fields. That means diamagnetic materials won't respond to magnetism. If you apply strong magnetism, they get repelled. And the most superconductors, okay, fine. Paramagnetic materials produce a little magnetism with them. So they are example aluminum, sodium, calcium, weak magnetism they are going to produce. And ferromagnetism, they form friendship and they form groups, yes, which we will call domains. So elements will form groups with the subsequent atoms, and they form strong localized magnetic regions inside the material, which we will call domains. And if you heat a ferromagnetic substance, then it will become paramagnetic substance. At which temperature ferromagnetic substance becomes paramagnetic substance is known as Curie temperature, and the corresponding law is Curie's law. Chi is inversely proportional to T, and of course this is Curie's law. And cobalt, iron, nickel are ferromagnetic substances examples. Next, mu r is very high. Relative permeability is high for ferromagnetic substances. Hysteresis loop. Before going to this, I want to tell you something more, that is susceptibility, diamagnetic material, paramagnetic material, ferromagnetic material. Susceptibility, chi. Chi value is negative and small. Negative, small. This is positive and small. Chi value positive only but large. Can be magnetized high. Susceptibility. And relative permeability is this is very large, very high. Relative permeability is very high, and these are just greater than 1, these are less than 1. Relative permeability less than 1. Okay, small numbers will come, point numbers like that. Next, hysteresis loop. If you apply magnetism to a material, it may not magnetize subsequently or immediately. It maintains a lag. It maintains a lag. The lag or lagging behind, I lags behind H is known as hysteresis. And this is a BH curve or IH curve. Both will be same only, just on multiplying with mu. Ferromagnetic materials will have large area like this. They are permanent magnets. If the area enclosed by the graph is less, then they are less permanent magnets. They can be used for temporary magnets. That means whenever you magnetize, they won't follow immediately. So that lag only called hysteresis. And less hysteric means immediately magnetizable material. Strong hysteresis means they follow the lag. Immediate, even demagnetization is also difficult for them. Magnetization difficult, demagnetization also difficult. So more hysteresis for a material indicates more energy loss. Yes. And high area indicates large retentivity and large coercivity. Hard magnetic materials are, that means strong magnetic materials are large coercivity, large retentivity, large area of hysteresis loop. Used to make permanent magnets. Alnico, aluminum, nickel, cobalt, and steel, and so. Soft magnetic materials are small coercivity, large retentivity, and small area of hysteresis, used for temporary magnets and electromagnets. Electromagnets are made up of ferromagnetic materials which have high permeability and low retentivity. Soft iron is a suitable material for electromagnets. Electromagnets are used in electric bulbs, electric bells, not bulbs, buzzers, actually electric buzzer, loudspeakers, and telephone diaphragms for receiving as well as producing sound. Giant electromagnets are used to lift machinery and bulk quantities of iron and steel, shipping from ship to outside to ship and in the factories. Earth's magnetism. Earth magnetic field can be resolved into perpendicular components, into two perpendicular components. They are, one is horizontal component of Earth along the surface of the Earth, other one is vertically inside or outside, depends upon the hemisphere where you are. And BH is equal to B cos del, BV equal to B sin del. This is the vertical component, this is the horizontal component, and B is inwards. Next, magnetic dip. That means if you suspend a bar magnet, then it won't be horizontal to the surface of the Earth except at the magnetic equator. It will be dipped like this. So that angle made with the horizontal is dip angle, that is magnetic dip, whose tan is given by tan del is equal to BV by BH. At poles, del is equal to 90 degrees, BH is equal to 0, BV equal to B. And at equator, del equal to 0, BH equal to B, BV equal to 0. Next, electromagnetic induction we are going to discuss. Electromagnetic induction structure is this one. Experiments of Faraday, Henry, and magnetic flux, not flux, magnetic flux, Faraday's law of induction, Lenz's law, conservation. Maybe the typist is non-mathematics students, non-science students. Conservation, non-conservation. See, I can't see like this. I'll edit it. Motional electromotive force, motional EMF, and inductance, AC generator. Okay, I'll convert it later. Now only I would like to convert. Just a minute of task it is. Faraday's law. Faraday and Henry, magnetic flux. And conservation. Conservation of energy. Yeah. Conservation. Yes. Flux. The phenomenon in which electric current is generated by varying magnetic fields is called electromagnetic induction. Variable magnetic field associated with a coil will produce electromagnetic force EMF. This phenomena is known as electromagnetic induction. Flux linked with a coil is given by phi is equal to B bar dot A bar or BA cos theta, and if the field is non-uniform, then phi B equal to integral B dot dA. Faraday's law of electromagnetic induction. The very first law is whenever the magnetic flux linked with an electric circuit changes, it causes induced EMF in the coil. The induced EMF exists as long as the change in the magnetic flux continues. Once the change in magnetic flux stops, then EMF will become 0. Next, second one, the magnetic field magnitude of induced EMF is directly proportional to the rate of change of magnetic flux associated with the circuit. So E is equal to N d phi by dt, that is equal to N BA cos theta with a derivative d by dt of N BA cos theta. Any one can be changed, number of terms can be changed, B can be changed, A can be changed, theta can be changed. Conventionally we are changing theta only. Next, the negative sign indicates the direction of induced EMF is in such a way that it opposes the cause of it, which is called Lenz's law. Lenz's law gives this negative sign. The average induced EMF when a magnetic field B is changed is given by E is equal to minus AN cos theta into B2 minus B1 by T2 minus T1 when field is changed, when area is changed, when theta is changed, when number of turns are changed. So like that for everything you can write. And induced current is equal to produced EMF by resistance will give you current I. Next, and if you are taking direct subtraction, that is average. If you are taking a rate of change, then that is instantaneous. The amount of charge induced in a conductor is Q equal to phi initial minus phi final by resistance. This is charge produced. And when a rod of length L is placed in a uniform magnetic field and moved with velocity v, then across its ends we are going to observe an EMF which is BLV, which we will call motional EMF, BLV. And if a rod is moved making an angle theta with its length, E is equal to BLV sin theta, and vector form is equal to EMF is equal to B bar dot L bar cross V bar, and it's just nothing but box ABC. You can change the respective things. If the rod is connected by an external resistance, I is equal to E by R, that is BLV by R. Force acting on the rod F is equal to BIL, which is force acting on the rod BIL, which is B square L square V by R. If V also wants a square, you can put so that it will become par. Par is equal to B square L square V square by R. Important formula, those are all. Without whom we can't do some instantaneous EMF in an AC generator is equal to NBA omega sin omega t, because it rotates the coil in the magnetic field with an angular velocity omega. So ban omega sin omega t, it's a sinusoidal function if you rotate a coil in a magnetic field. Fleming's right hand rule is used to have the polarity of the EMF and the current. And motional EMF in rotating a rod in a magnetic field is given by E equal to half BL square omega. And if disc is rotated whose radius is R, then EMF from center to the edge is half BR square omega. And self-induction is given by the formula E is equal to minus L di by dt, where L is known as self-induction of the coil. This is actually another concept immediately started. Self-inductance of a circular coil is given by mu naught pi n square R by 2. Actually N1 N2, if both are very close, then n square we will write. Self-inductance of a solenoid is mu naught n square AL, or n is equal to n by L, so that mu naught n square by L into A. Here A only, pi R square sometimes we will write later. Energy stored in inductor is equal to half Li square, where I is the current and L is self-inductance. And magnetic energy stored per unit volume is half B square by mu naught. Electrical energy stored per unit volume is half epsilon naught E square. These two usually we use with electromagnetic wave, EM wave. Inductors in series, if whenever several inductances are connected in series, effective inductance is equal to L1 plus L2 plus L3 and so on, as E equal to E1 plus E2 plus E3 and so on. If they are in parallel, 1 by L equal to 1 by L1 plus 1 by L2, that is followed. Next, mutual inductance. When two separate coils are placed side by side or close in the vicinity, and if they can be coupled with a magnetic field produced by one of the coil, then the other one also gets induced EMF, and vice versa. This is mutual induction concept, and mutual inductance will give you phi is equal to MIP, primary current change causes flux change in the secondary. So phi is equal to MIP, where that quotient is known as mutual inductance. This is its units also Henry only, and M is equal to phi S by IP. Actually d phi S by dip. Change in current only, a good one. Next, quotient of mutual induction, mutual inductance is given by with that EMF produced in the secondary coil is given by E in the secondary coil equal to minus M into dip by dt. This is current change in the primary coil. Rate of current change in the primary coil causes a proportional EMF in the secondary coil. Mutual inductance for long coaxial solenoids is mu naught N1 N2 by mu naught N1 N2 into A by L, and this is M minus actually root L1 L2, right? Relation between mutual inductance for two coils is M minus root L1 L2. Growth and current in an inductor resistance circuit with alternating current application, I think so. So when current I is in a circuit, I is equal to I naught 1 minus e to the power of minus t by 2. This is when a battery is connected, DC circuit, LR DC circuit. When a battery is connected to LR circuit, then maximum current is I naught. Then I is instantaneous current, which is given by 1 minus e to the power of minus t by 2. And lambda equal to L by R, called inductive time constant, and t equal to lambda, that means inductive time constant. In that time, here it will become 1 by E, because I is equal to I naught e to the power of I naught of 1 minus e to the power of minus t by tau, or I will write this formula. This is different actually. I is equal to I naught of 1 minus e to the power of minus RT by L should come actually. Okay, R by L by R is known as tau or lambda. That should come here. It's an error. That's what. It's not registering in my mind. I'm just reading. I understood now. Now I is equal to I naught of 1 minus 1 by E, that is 0.63 times of I naught at decay constant, inductive time constant time. Next, decay of current. When current is discharged through a good conductor from an inductor, then current at any instant is given by I naught e to the power of minus, this is wrong actually, this is I naught e to the power of minus t RT by L, RT by L, or people will write I naught e to the power of minus t by tau or lambda. Here lambda we are using, so lambda only you can put, not a big task. Tau is also good one, 0.37 if what you call the time lapse is L by R, that means lambda time, then e power minus 1 will come, e power minus 1 value 0.37, so 0.37 times of I naught or 37% of I naught. Growth of charge in a capacitor resistor circuit is CR-DC circuit. Growth of charge is, even this one also typed wrong, this is also, this formula is Q is equal to Q naught of 1 minus e to the power of minus t by CR actually, this is CR, this is RT by L, this is CR. Okay, so next CR. This is also wrong. This is equal to Q naught e to the power of minus t by CR. That is in growth 1 minus e to the power of minus t by CR. In decay e to the power of just minus t by CR. No 1 minus. In growth 1 minus will be there. In decay there is no 1 minus. LC circuit oscillations with angular frequency omega equal to 1 by root LC. And LC circuit oscillations with frequency f equal to 1 by 2 pi root LC, correct only. And whenever LC oscillations, it is used to convert direct current into alternating current. It will produce an alternating things. So its frequency is 1 by 2 pi root LC. Charge on capacitor at any time t is equal to Q naught cos omega t. Current in inductor at any time is t is I is equal to dq by dt, I naught sin omega t. Electrical energy stored in capacitor U is equal to Q naught square by 2C. Magnetic energy stored in inductor is half Li square. And with this formula we can do majority sums. Keep on practicing the formula and we'll do sums in the next subsequent sessions. Bye.